The earth beneath our feet feels solid, unyielding. We build houses, cities, entire civilizations on its surface, taking for granted its stability. But this stability is an illusion. The Earth's surface, far from being static, is in a constant state of slow, relentless motion. It's like a jigsaw puzzle, but one where the pieces are always shifting, grinding and pulling apart. Imagine a world where continents drift, oceans open and close, and mountains rise from the depths. This is not the stuff of fantasy novels, but the reality of plate tectonics, a scientific theory that revolutionized our understanding of the planet we call home. It's a story that spans millions of years, a tale of immense forces shaping and reshaping the Earth's surface. The theory of plate tectonics tells us that the Earth's outermost layer is not one solid piece, but rather a mosaic of giant slabs called tectonic plates. These plates, some as large as continents, float on a layer of hot, partially molten rock in the Earth's mantle. It's the movement of these plates, driven by the Earth's internal heat, that creates the dynamic geological processes we see around us. To understand plate tectonics, we need to delve beneath the surface into the Earth's interior. Imagine the Earth as a giant apple. The thin skin of the apple represents the Earth's crust, the outermost layer. The crust is divided into two types: continental crust, which forms the continents, and oceanic crust, which lies beneath the oceans. Beneath the crust lies the mantle, the thickest layer of the Earth, represented by the fleshy part of our apple. The mantle is not a solid mass, but behaves like a very viscous fluid over geological timescales. It's hot down here, heated by the Earth's core, and this heat drives the movement of the tectonic plates above. At the very center of the Earth lies the core, the apple's core. The core is divided into two parts, a liquid outer core and a solid inner core. The core is incredibly hot, reaching temperatures of over 5,000 degrees Celsius. It's the intense heat from the core that drives the convection currents in the mantle, which, in turn, move the tectonic plates. The Earth's tectonic plates are in constant motion, albeit very slow motion. They move at rates of a few centimeters per year, about the same rate as your fingernails grow. It might not seem like much, but over millions of years these tiny movements add up, causing significant changes to the Earth's surface. The movement of the plates is driven by convection currents in the mantle. Hot material from the Earth's interior rises to the surface, cools, and then sinks back down, creating a continuous cycle of heat transfer. This cycle drags the tectonic plates along with it, like rafts on a slow-moving river. The interactions between these moving plates are what create the Earth's most dramatic geological features. Mountains rise where plates collide. Volcanoes erupt where molten rock from the mantle finds its way to the surface, and earthquakes shake the ground where plates grind past each other. The idea that the Earth's continents might be moving is not new. As far back as the 16th century, map makers noticed that the coastlines of South America and Africa seemed to fit together like pieces of a jigsaw puzzle. But it wasn't until the early 20th century that a German scientist named Alfred Wegener proposed a radical theory to explain this observation. Wegener called his theory continental drift. He proposed that the continents were once joined together in a single supercontinent he called Pangaea, surrounded by a vast ocean. Over millions of years, Pangaea broke apart, and the continents drifted to their present positions. Wegener's theory was met with skepticism from the scientific community at the time. He lacked a mechanism to explain how the continents could plow through the solid ocean floor. It wasn't until the discovery of seafloor spreading in the mid-20th century that Wegener's ideas were finally accepted. Section 5: Clues from the Past. Wegener, however, persisted, gathering evidence from various fields to support his theory. He pointed to the remarkable similarity of fossils found on continents now separated by vast oceans. For example, fossils of the Mesosaurus, a freshwater reptile, are found in both South America and Africa, suggesting that these continents were once joined. He also noted the alignment of ancient mountain ranges and rock formations on different continents. The Appalachian Mountains in North America, for instance, share geological similarities with mountains in Scandinavia and Scotland, suggesting they were once part of a continuous mountain chain. Wegener's most compelling evidence came from the study of ancient climates. He found evidence of glaciers in tropical regions of Africa and South America, suggesting that these continents were once located closer to the South Pole. He also found evidence of tropical coal deposits in Antarctica, indicating that this now frigid continent was once located in a warmer, more temperate region. Section 6. The ocean floor unveiled. The missing piece of the puzzle fell into place in the 1960s with the discovery of sea floor spreading. Scientists using sonar to map the ocean floor found a vast underwater mountain range, the Mid-Atlantic Ridge, running down the center of the Atlantic Ocean. They also discovered that the rocks on either side of the ridge were symmetrical and became progressively older further away from the ridge. This discovery led to the realization that new oceanic crust is being created at mid-ocean ridges, where molten rock from the mantle rises to the surface and solidifies. As new crust is generated, the older crust is pushed away from the ridge, causing the seafloor to spread. This process of seafloor spreading provided the mechanism for Wegener's continental drift. The continents don't plow through the ocean floor, they ride passively on top of the moving tectonic plates, like passengers on a giant conveyor belt. Section 7. When plates collide. The Earth's tectonic plates interact in three main ways. They move apart, they collide, or they slide past each other. Each type of plate boundary creates a unique set of geological features. At divergent boundaries, plates move apart, creating new crust. The Mid-Atlantic Ridge is a prime example of a divergent boundary. As plates pull apart, magma rises from the mantle to fill the gap, creating new oceanic crust. This process is often accompanied by volcanic activity and earthquakes. Convergent boundaries, on the other hand, are where plates collide. The type of collision depends on the type of crust involved. When two oceanic plates collide, one plate is forced beneath the other in a process called subduction. This process creates deep ocean trenches and volcanic island arcs, such as the Mariana Trench and the Aleutian Islands. Section 8. Shaping the Earth. When an oceanic plate collides with a continental plate, the denser oceanic plate is subducted beneath the continental plate. This process creates volcanic mountain ranges, such as the Andes Mountains in South America. The collision also causes the continental crust to buckle and fold, creating mountain ranges like the Himalayas, where the Indian plate is colliding with the Eurasian plate. At transform boundaries, plates slide past each other horizontally. The San Andreas Fault in California is a well-known example of a transform boundary. The movement along transform boundaries is often jerky and unpredictable, leading to frequent earthquakes. The theory of plate tectonics has revolutionized our understanding of the Earth. It explains why earthquakes and volcanoes occur in specific locations, how mountain ranges are formed, and how the continents have moved throughout Earth's history. Section 9. A dynamic planet. Today, scientists use a variety of methods to monitor plate movements and study the Earth's interior. Satellites equipped with GPS technology can track the movement of tectonic plates with millimeter precision. Seismographs measure the vibrations caused by earthquakes, providing valuable information about the Earth's internal structure. The study of plate tectonics is an ongoing process. Scientists are still working to understand the details of how plates move, how plate boundaries evolve, and the full impact of plate tectonics on Earth's climate and evolution. Plate tectonics is a powerful reminder that our planet is a dynamic, ever-changing system. The Earth beneath our feet is not static, but is constantly moving and evolving, shaped by the immense forces of plate tectonics. Understanding these forces is essential for predicting and mitigating natural disasters, managing our resources, and appreciating the incredible planet we call home.